I see.
Thank you. Very good evening, friends. Happy to be back with you all today in this series of tech talks from Mahindra, hosted by NPTEL, under the theme Mobility Engineer 2030. So, sure, some of you might have participated in a few of the other talks in this series earlier. And today, the focus is on automotive materials technology. And I have brought two of my senior colleagues here who are experts in materials, automotive materials, to share their knowledge with you today. And just give me a moment so that I will share my presentation and then we'll get started. Just give me a minute. So I hope you can see my screen. The topic for discussion today is advanced materials technology for mobility engineers. And we have Dr. Guru Shankar Rajan, Mr. Balaji, and myself, Shankar Venugopal, with you here for the next 1 hour to discuss about this. And this is, as I mentioned to you, this is the 8th talk in the series, and we have 2 more talks to go. And the last time we spoke, it was on systematic innovation based on TRIS, and that was on the eve of Deepavali. And today, we are going to focus on advanced materials technology. And I would request my colleagues to introduce themselves at this stage. So let me hand it over to Dr. Guru Shankar Rajan to introduce himself. Over to you, Dr. Guru.
Thanks, Dr. Shankar. Good evening, all. I am Guru Shankar Rajan, as Dr. Venugopal Shankar explained. I am heading the materials technology team at Mahindra Mahindra, responsible for metals, plastics, composites, elastomers, coatings, adhesives, and advanced materials technology projects. I did my PhD at the University of Cincinnati, focusing on plastics and elastomeric nanocomposites, followed by a postdoctoral associateship at the University of Southern Mississippi with experiments on polymer magnetic nanocomposites. Following that, I worked in a small business innovation research company and moved back to India, joined Tata Autocom, Interiors and Plastics Division. And then I was at Fiat Chrysler for about 8.5 years before joining Mahindra. That's my background. Thank you, Dr. Shankar. Back to you, Dr. Shankar.
Thanks, Dr. Guru, for joining us today. We look forward to your introduction to the world of automotive materials. Thanks so much for sparing your time for this session today. Let me also introduce to you my other colleague, Mr. Balaji, who is an expert in composites for automotive application. So let me ask him to introduce himself to you. Over to you, Balaji.
Hello all, this is Balaji. It's a pleasure to meet you all virtually. I am a materials engineer. I'm working in the domain of automotive materials. Here in Mahindra, I'm the lead for plastics, composites, soft trim, and polymer lab. Coming to my overall experience, I started with corrosion management, composites, adhesives, and then later on went on to working in the domains of plastics, rubbers, and today I am working focusedly on the domain of plastics and composites, soft trim. That's brief about me. Over to you, Dr. Shankar.
Yeah. Thanks, Balaji. So Balaji is also a very active inventor with patents to his credit, and is also currently pursuing his PhD at the university abroad in the field of automotive composites. So thanks, Balaji, for joining us today. So with this, let me just give you an outline of what we are going to cover. For those of you who have not attended these talks earlier, let me introduce myself. I am Shankar Venugopal. So I'm the Vice President handling technology innovation and knowledge management. Also the Dean of the Mahindra Technical Academy. I've been with Mahindra since 2017. And prior to joining Mahindra, I worked with for Cummins, Honeywell, Dow Chemicals, General Electric, and also the Indian Space Research Organization. By way of education background, I studied physics and did my PhD in material science from the Indian Institute of Science, Bangalore. And I also did my management education from the Indian Institute of Management, Bangalore. I'm a prolific inventor with a few granted patents and also a bunch of patent applications in the pipeline. And I'm a TEDx speaker and I love to speak on technology and innovation topics. So the plan for the talk today is in three parts. The first is the introduction to the world of automotive materials by Dr. Guru Shankar Rajan, followed by a session on composite materials, the design and application by Mr. Balaji. And then I will come back and handle a session on the materials for electric vehicles. So this is the plan for the day. And what I'm going to do is move to the first part, which is introduction to automotive materials. At this stage, I'm going to stop sharing so that Dr. Guru can share and go ahead with this module. So over to you, Dr. Guru. You can share your screen and go ahead with your module. Yes, we can see.
Good evening, all again. Thanks for the introduction, Dr. Shankar. Introduction to automotive materials. This is a very, very exciting time to be in the automotive industry, particularly in India, where we are having a lot of challenges. There are a lot of driving forces that is making India very innovative and frugal in the terms of engineering to bringing materials to part and to the vehicle. Now, let's see what some of those driving forces are. For example, weight reduction, vehicle efficiency, and alternate fuels. Well, all these contribute towards a goal of achieving lighter vehicles, increasing the mileage, and also innovation in terms of what other fuels we can bring into the industry. And the background, we have the greenhouse gases, zero emission vehicle, CAFE norms, life cycle management, which is very important, and of course, sustainability in terms of the environment as well as the economic environment of the industry. So these are some of the driving forces. We can bucket this as environmental and regulatory. And the next bunch of forces that are driving the industry are IDAS, integrated safety and driver assistance, user experience, HMI, and connectivity. So the next generation of vehicles, you will find a lot of these in place where the industry as well as the customer demand is pushing innovation. And the third thing is very important to the customer, comfort and convenience. How do they perceive the quality, the seat structure, the seat material, the soft touch, some of the things that are very important to the customer, and of course the appearance. So to summarize this slide, what we want to understand is what are the driving forces and how do we make materials perform those functions that are required to satisfy the customer. Now, once the driving forces are established, we need to have a strategy. And this is mainly for selecting materials for automotive applications. First thing we need to comply with is the regulatory requirements, and this is very important that we have to comply, unless in other ways we cannot launch the vehicles. And India is moving forward with a lot of these requirements. Then we have the engineering requirements, performance, durability, and reliability. And how do we pack all these components into the vehicle? That is very, very important. That way we don't have interface issues. Business requirements. We will not be able to achieve everything in a vehicle. So there is a brand, there is a model, and there is a variant. So based on the business requirements, the engineering requirements are bucketed, and that will satisfy the business requirement, and of course cost being one of the key factors. Not but the least, we have the customer requirements. As explained in the previous slide, the customer now is demanding that they have IDAS, they have the soft touch, they have comfort while seated, while driving, while they are in the third row, the AC, and so forth. There are a lot of things that the customer demand, and a material is selected based on those requirements as per the brand and the variant. Now, I'm not going to dwell on the material properties. However, just to give you a glimpse on where the modulus versus strength and strength versus density map follows. So if we want to have a high modulus and high strength material, usually the tendency is go towards metals. And now the carbon fiber composites are catching up. As you can see at the top right corner, just below metals, that they are catching up with metals. And of course, we have polymers, which are plastics. And for some of the applications like hoses, seals, we have elastomers. And for seats, seats, we have foams, and also for noise and sound absorption. And on the right side, you have strength versus density. Of course, if you go to steel, it has higher density compared to that of a plastic or composite. And within metals, you have steel and aluminum. Aluminum has about 1/3 the density of steel, and composites are even lower depending on how much you load. And plastics have about a density of 1 to 1.5 depending on the filler content. So this is just to give an idea about where we are in terms of materials and their properties, and we can select materials from this. This is not an exhaustive material property slide, but it just gives you idea about where we fall in terms of metals versus polymers. Jumping into the trends in automotive industry, this is a material content in mass market car, a typical vehicle that is available in the US and Europe and Japan. You can see that iron, mild steel, and steel, high strength steel, is still dominating. About 70% of the mass is from these materials. Aluminum is catching up, so does plastics and other materials. But if you move from a traditional vehicle made out of steel to a vehicle like BMW i3, you can see the trend is reversed, where the plastics and composites are used almost 60%, and of course aluminum and steel are also used. Now, with the weight reduction, there are a lot of advantages, and some of the technologies in composites Balaji will cover in the next presentation. But this is the trend, and I will show you in the next few slides how the trend is also working out for multi-material vehicle strategy. So in metals, again, we have advanced high strength steel, ultra high stainless steel, strength steel, and then aluminum playing a major role in taking up majority of the body in white and the closures, what we call doors, hoods, taking up most of the weight. You have mild steel, AHSS, UHSS, and aluminum. Of course, there is magnesium, some use in CCBs and also in some of the closures as an inner panel. Now, that was from Volvo, and now we have Ford, which has already introduced aluminum in a larger content and also saved up to 700 pounds in their pickup truck. So you can see the trend that this is again from Audi. This is again a mix of steel and aluminum. And you can see that it's a multi-material vehicle built on steel and aluminum in BAW enclosures. Now moving on to trends in composites, SMC, the sheet metal compound, has been used for a long time to make almost the entire door panel and all the closures. You can see this is a Corvette, GM Corvette, that has SMC with glass fiber and also with carbon fiber all over the body components. This is a trend. This has been going on for 20-30 years now. And this is a Jeep Wrangler. The hard top is made out of SMC. And of course, some of the pickup trucks have a pickup box, a cargo box, and also the in-bed trunk. In this one, you will see that it's very interesting that they're using different technologies again, as part of the vehicle or the component. DLFT is nothing but direct long fiber technology. So they're using a little bit of that. They have sheet molding compound SMC, and these are unpainted, meaning the color is given in the material itself, and they have eliminated painting. So this is the trend that is now prevailing in the automotive industry, where steel, aluminum, magnesium, plastics, and composites are used for body in white, chassis, and all the closures. So this is very important as we go forward, that an automotive equipment manufacturer, the original equipment manufacturer, has several materials. There will be challenges, but this is the way the industry is trending right now. And Finally, we have the carbon fiber composites. You can see the body in white, which can be easily lifted. It weighs about 120, 140 kilograms compared to a traditional body in white, which might be 350, 400 kilograms. And recently, I think it was 2019, last year, September, October timeframe, again, GM has introduced a pickup box where again they are using not just composites but steel, plastic, and aluminum to give it more weight saving as well as better dent properties, dent resistance, better corrosion resistance, and other properties that are required for the pickup truck to perform. This is carbon fiber reinforced thermoplastic material. This is not a thermoset composite. And this is how you see the vehicle, and it stands out and it performs well. Now, having seen some of the materials and the trends, it's very important to understand what the challenges are. We cannot go and just replace one material with another material, but we have to design for that specific material to get weight and cost saving. If we are focusing on a composite where we can eliminate multiple metal parts, it has to be designed for that so that we can save on the tooling cost and we can reduce the weight. And at the front end, most of the work should be done with modeling, meaning simulation, virtual engineering, and the design has to be verified so that the protos that are built are lesser in number and the success rate is higher. We have to ensure that the part that has come from the material is actually designed for manufacturing, designed for assembly. And once we have some repair, some damage to the vehicle, to the part, how are we going to detect and repair the damage? That is something that we have to be aware and we need to have a plan in place. And of course, some of these materials are not available in India, it has to be imported. So we have to work on some of the issues that we might face later. To sum up, we have to be ready for a strategy in the entire ecosystem where the raw material is available in India. If not, how can it be localized? How can it be made in India? How do we bring the raw material to part? Because some of the issues that we face in tier 1 and the tier 2 is on converting the raw material to a part that is defect free. The quality is to the highest standard and rework is to the minimum. Once we have established the entire chain, it will be industrialized. And that should be the focus when we select a material, when we innovate a material. And when it goes to industry, when it's commercialized, that's when you see the true benefits of either it's aluminum or composite or magnesium. Whatever the material is, only then you'll see the benefits. So there are some driving forces as explained in the initial stages. Then you select a material based on design, and for that particular application. And once you choose that application and the material, it's very important that you follow the ecosystem and ensure that everything is available. So those are the challenges that you will have in commercializing these materials to the automotive parts in India. Of course, there are several examples, successful stories in India and within M&M. Maybe that is for some other lecture. But today, this is just to give you an idea about what the trends are and what the challenges are. Thank you. Now, Balaji will take over for a specific topic on what I described earlier, composite materials. Back to you, Balaji.
Thanks, Doctor. I'm just presenting, sharing my screen. Is it visible?
Yes.
Yeah. So good evening all again. Thanks, Doctor, for that wonderful session on material selection and the overall trend on automotive materials. The next few minutes, I would like to spend more focusedly on discussing composite materials, the key applications, and just a design methodology. So, why composites? That's a question which everyone will ask when there are multiple options to choose from, ranging from steel, aluminum, magnesium, and even new age materials. Why specifically composites? So we will talk on that, and then we'll move on to the initial successes and future trends, and then we will discuss a bit on the composite design methodology with some examples. Finally, we will conclude this particular part by discussing on the key challenges that we face in composite design and application. Yes. So, Dr. Guru showed you this slide. Yes, that's the trend. Mass market car traditionally uses about 70% steel, but then we have some cases of composites dominating the material content in a car. BMW i3 is a classic case. There are multitude of reasons on why this trend happened. That's precisely what I'm going to show. The next slide. Yes. So the first dominating reason on why to go for composites is range improvement. In the previous slide, you would have noticed that a BMW i3 had used 55% composites. Now they had to use it because composites, owing to their unique property profile in terms of specific strength, stiffness, they have the capability to reduce the weight of the vehicle, as a result of which the range, the fuel economy can be improved. So that is one primary reason on why composites are getting preference over conventional materials when it comes more specifically to a hybrid or an electric drivetrain. Now, the other reason is, just you could see the right side image, wherein there is a downsized hybrid or electric drivetrain. This calls for a unique packaging. How do we package all this within the available space so that we can use the upper body efficiently. So how do we do that? Again, design flexibility is the need there, and composites have been known to have excellent design flexibility. You can design complex profiles using composites. So I would like to draw a parallel here. When we go for buying a car, who makes the buying choice? It's usually the family, and looks matters, right? And certain aspects were usually delivered by plastics and composites, like design contours, the curved profile. Those are all very easy to make with composites. So thereby, the trend is the car is being considered as a fashion accessory, like our handbags and wallets. People also try to show their fashion sense in cars. So again, composites make that possible. And finally, as was mentioned in the preliminary discussion, the emission norms. Yes, we need to meet the emission norms with more focus on climate change. So here again, composites play a huge role because of their lightweight. They help in reducing the fuel economy. They're reducing the emissions and improving the fuel economy so that we get maximum benefits out of composites. Moving on, what are composites? Well, now there was a time, when I recall people in India used to refer composites as fiber. They will, for them, I recall an incident wherein when someone had wanted to, just as a layman, when they want to experience a vehicle, they will just do a tuck tuck, and if there is a metal, they'll feel happy, and if it's any other sound that comes out, then you would have seen people's emotions changing. Oh no, it's a fiber, which means it might not have the desired strength, it might not have the desired stiffness. So there's always this flimsy feel that was associated with composites. On top of it, the insurance companies were also paying less insurance for the composite parts. Even today, we can't get 100% insurance for our bumpers unless it's a bumper to bumper insurance. People normally go only for 50% insurance. So that was how the feeling was when it comes to composites. And I would say that it's only a perception. Out here in this slide, you will notice that there are two broader type of composite materials, the thermosets and the thermoplastics. And thermosets are basically material composites that are made out of a combination of thermoset polymers like epoxy, vinyl ester, unsaturated polyester, in that order of strength requirements. And then we also have the reinforcements in terms of glass, carbon, aramid, and there is a huge area of future fibers which are getting explored, like conventional fibers are getting replaced with natural fibers like jute, kenaf, sisal, bamboo, and this whole gamut of natural fiber composites are coming up in a big way. To add on it, with the introduction of nanomaterials, ever since Iljima discovered carbon nanotubes in 1991, and since graphene was discovered in 2004, since that time, a lot of focus has been made in using these nanomaterials alongside the synthetic and natural fibers. Thereby, composites have started replacing conventional materials in a lot of structural applications. On the other side, recyclability, the perception that we are polluting the environment has led to the advent of thermoplastic composite materials. This is not something new. People have been using thermoplastics for quite some time. As you could see, the primary thermoplastic materials that are there comprise the commercial materials like polymers like polypropylene, polyamides, which are colloquially called nylons. And then we also have polycarbonates, which are used for things like the spectacle lenses, the headlamp lenses. So these materials are combined with, again, synthetic or natural fibers and nanomaterials to give what is called a hybrid material that has yeah, a long fiber or a short fiber and a nanomaterial. So this gamut has grown over a period of time, thereby shattering the age-old perception that composites are flimsy and they might not be suitable for structural. Today, yes, confidently we can use composites for structural applications, as was displayed in the previous chart wherein BMW i3 had used that in a big way. Now, having talked about basics of composites, how are they manufactured? Well, today, as you could see, there's a gamut of manufacturing methods for both the thermoset and thermoplastic composites. We started with the conventional hand layup for a thermoset composite material. Boat hulls were used to be made out of hand layup method. Still, people use boat hulls, boats made of hand layup process. Then we have all the tankers, which we use for carrying oils, water tanker, that water tanks. And then we have our RMC ready mix concrete tankers. Those are all made of a process called filament winding. And then moving on, we have the advanced composite technologies like resin transfer molding, a lot of aerospace, space applications. They use resin transfer molding, prepregs. Basically, prepregs are a category of material within thermoset composite that has a pre-cured resin along with the reinforcement, which can be pressed or formed into a shape. So these are the staple of a race car industry, of aerospace parts, and also for space. Now, in automotive, because of the volume requirement, because we have to make a lot of cars for many customers, and all the cars have to be consistent. So, coming from that perspective, sheet molding compound compression molding is one such process which has given great advantages to the automotive industry. And then we have another very high advanced manufacturing process, which is catching up very highly lately, which is the high pressure resin transfer molding. Now, the advantage of this is that we can make a part in few minutes, a big part in few minutes. So I will detail some of these in the upcoming slides. That is on the thermoset side. Now, on the thermoplastic side, again, a lot of innovations and technology upgradation. We start with injection molding, which is a very basic level of the processing, thermoplastic processing, plastic processing rather, I would put it. But then still, it is a widely used and the most popular because of the amount of experience that we all have gained out of that process. Then moving on, we have the in-mold compounding or the direct line and coupled with the direct long fiber injection. Now, this technology is a step over the injection molding, wherein in case of injection molding, what we do is we take a plastic compound, a thermoplastic mix, and then we mold it into articles. Those are two separate unit operations. Now, in case of in-mold compounding direct long fiber injection, what happens is the machine has been made in such a way that at one end, the compound is made or the mix is made, and simultaneously, once the mix gets conveyed, and then we get the part in one shot. So this has saved a lot of energy, a lot of time, plus the most important is it has improved the overall strength of the composite. Now, the next thing is thermoforming. Injection molding is the next process, the current upcoming process, which again has got a lot of attention the world over. That GM Denali pickup box, which was showcased in the first part, was a thermoplastic injection molding and with blank stamping. So these are some of the thermoplastic composite materials. Now, another key variant here is when we think about thermoset composite materials, the reinforcement plays a major role in any composite, but more specifically in thermoplastic composite. The reinforcement comes in various sizes. So we have a short fiber, we have a long fiber, and then we have a continuous fiber. So the reinforcement is the load carrying member in a composite. So depending on the technology to maximize the fiber length, the complexity of the technology varies, and finally the continuous fiber mat is the aim, which gives the maximum property advancement. That's the reason why you will notice that the injection molding, the fiber length distribution will be very less. That gets enhanced in the in-mold compounding direct long fiber injection. And then moving on to thermoforming or blank stamping, we can get a continuous fiber mat impregnated with a thermoplastic resin. This will give the maximum strength. Similarly, on the thermoset side as well, we have all these methods to know in that order. Filament winding, we have a continuous fiber reinforcement, and in terms of resin transfer and in sheet molding and high pressure, we use a lot of continuous fiber mats. Thereby, we can do away with that mindset that it is flimsy. Moving on, what are the properties that make composites attractive? So high specific strength, high specific stiffness, that's there. Toughness is also very high for composites. It offers corrosion resistance, wherein we can. This is an area which is of much relevant to coastal areas. So we can replace cabin parts with composites and be free from corrosion issues. And then it's an attractive life cycle costs. Now, there are published studies on this particular aspect, that when we compare the cost of a sheet metal part with a glass fiber reinforced polypropylene part, which is a thermoplastic part, it might appear that the use phase costs or the vehicle's usage, which the customer can see, is actually lower for sheet metal as compared to glass fiber plastic. But then when we see the overall life cycle, that includes the material manufacturing cost, the usage plus the recyclability costs, there's a published study that says that glass fiber reinforced thermoplastic scores better than sheet metal. So that is one more advantage of using composites. And the last three are the current trending ones. Composites can be made electrically conductive or thermally conductive when we add nanomaterials to the whole mix. Typically, nanomaterials like carbon nanotube or graphene can impart electrical conductivity, thermal conductivity to the composite, which means we can do inline sensing. So we can, in this age of connected connected cars and damage control, repair sensing, we can do an inline monitoring of the composite part, like how we monitor the tire pressure. We can monitor the performance of the composite part by having these materials as sensing units. And then with the whole focus on sustainability, with a lot of points discussed in the open media about how plastics are polluting the environment, now almost everyone have started working on having composites from renewable or biodegradable sources. So like polylactic acid, that is one polymer which is completely biodegradable and compostable. Now when that is combined with a natural fiber and with the nanomaterial, then we get a completely renewable composite which will not pollute the environment. So by this, composites are also finding a lot of traction in sustainable areas. So now, having discussed about what composites are, technologies, and what are their attractive properties, let us go through some applications. These are the initial successes. a front-end carrier. Now, this front-end carrier comes in the front of a vehicle, just behind the bonnet, behind the hood or the bonnet. Just behind that, there is a part called firewall. It comes before that. Now, the typical function of this front-end carrier is that it will house all the other systems, like radiators will come and fix in that in this part. Other system integration is being done here. Just imagine how costly it will be to do this in a metal with multiple welds. So the point here was composites have made these possible by injection molding as a manufacturing process. So we have that as one success story. Those were initially done probably in the last decade. Then we have an online paintable fender. Now, the front end of a car, as I mentioned, is a designer's choice. The designer wants to give a lot of design elements, a flexible design, so that we follow a fluidic design or we give an aesthetic appeal to the overall car. So fender is very critical from that, and plastics and composites have enabled this particular application. Finally, composite tailgate. Now, this is an area where, again, because of the design flexibility, what has happened is it has led to additional benefits. Now, we discussed lightweighting as one chief goal of using composites, but then because of this part design flexibility, it has also helped in reducing the coefficient of drag. Now, this has helped in the aerodynamics of a car so that, again, we get additional benefits. So these are some of the initial successes that were done using thermoplastics. This slide talks about the thermoplastic composites in the last decade and running into the present decade. Now, from the thermoset side, yes, there are additional technologies like whatever I mentioned, like the SMC. Now, that has matured into a next step called an automated SMC. So, which is being used for making parts like glass epoxy based pickup box or a carbon epoxy based hood of a car. Now, what has changed? This is a schematic I have given of how the composite is typically manufactured. So, at one end we have the fiber coming in, and the other end we have the resin coming in, and we have the glass fibers coming in, and the other end we have the resin coming in, and together they get mixed. Everything is robotically done, and finally we get the entire thing is taken to a press. Mat is taken to a press where the press compresses, and then we get a part which is stacked. So everything is automated, and these are state-of-the-art factories which produce these complex parts consistently, part by part. So these are some of the initial successes that have come up in the domain of composites over the last 2 decades. Now, but then, is this the limit? No, the limit has stretched now. This has concurrently happened with the development in other vehicle technologies. Now, you take this space frame which is showed from a Hyundai Intrado. Now, precisely for the aerodynamic drag and to give that fluidic design, Hyundai has actually used carbon fiber based composites in making the frame, the entire frame of the car, to which the body panels will just come and be plugged in. Now, Hyundai has taken a stand that this will be the base for all the year. This is how they will be designing future vehicles. That's the power of composites. Other side, we have the composite body, BMW i3. Yes, could see 2 people lifting it, the same that Dr. Guru had explained in the first part. Yes, that's also possible. But then the below image of a bus, that's pretty interesting. Why it is so? You could see that this bus, is a composite bus. It's an all composite bus with no metal in it. And when I say no metal in it, it's like the body of the bus is made of composite to which metal portions are just ferruled in. Now, the advantage of this bus is that this can be this particular bus which was done by Proterra. This can be inductively charged. The drive mechanism is pretty different, unlike an electric or a thing. This is completely based on the inductive charging. Now, this was done for fixed routes, like a school bus route, which has a fixed route. So this is the disruption that is happening today. And this disruption is because of the advantages that we described. Number one, it's the lightweighting. Number two, and the fuel economy associated with lightweighting. Number two is the coefficient of drag reduction. Number three is the design freedom or the design flexibility. And number four is that we can make these things sustainable. That's the future. Now, again, some aspects of the future technologies. Wheels. We have talked about, we have seen wheel covers in plastics, but this is where the world is working on, complete wheels out of composites. Now, why this is done? This is done, again, because of the same advantages that I listed earlier. And thermosets are preferred for these applications because of their superior dimensional stability. Now, we all know how a wheel has to behave when we brake or corner, or when a brake pad temperature goes up. So for all these load cases, the wheel has to withstand. So that's why a carbon-based composite has been chosen for making this wheel, and now this is commercialized. So there's a company in Australia named Carbon Revolution that does this using a process called high pressure resin transfer molding. Now, below is a schematic which I have given, wherein, first I'll simplify this. A preform is made. A preform in the sense fiber orientation. The fibers are carefully laid, fabrics are carefully laid. When I say fabrics, they are like carbon fabrics or glass fabrics. They are carefully laid, and then the entire preform is robotically conveyed and formed. And from that, it is taken into a mold where the resin is injected, and then we get a part after curing. Now, this entire cycle happens in a few minutes. So all these parts, like wheels, floor pans, hood, roof, now these are big parts. Consistently, they can be made out of a composite in few minutes time. Just imagine the kind of, we'll be eliminating welding out of it, we'll be eliminating other conventional technologies that were used for making these parts. That's the power of composites. Moving on, with respect to thermoplastic composites, yes, we have seen this. Now these are being considered again for body panels. Like we have the the resin which is getting with the reinforcement is made into a semi-finished product, and then by using stamping, like how a conventional steel gets stamped, you can even make composite stamped parts. Now these can go into seats, beams, pillars, doors, and I have given the process schematic again, and there is an example of a conventional car which is now made into a thermoplastic composite car. So that's on the future. Now, moving on. Okay, now we have seen the advantages. How do we design a composite part? So there are two approaches. One is we have a thermoplastic composite approach, and then a thermoset composite approach. The criticality is to choose one among the two. So what helps us in making that decision? It's the cost or the volume of the part, the target, and then the performance targets, like how I mentioned for a wheel, dimensional stability is very critical. So we need to choose on which composite has the good dimensional stability. Is it a thermoplastic one or a thermoset one? So that decision, the performance targets govern. Third thing is the function, the basic function, and the design failure mode effect analysis of how the part is going to function and be used. So all these three help us in defining on whether should we choose a thermoplastic composite route or a thermoset composite route. Now, once we have chosen this, we need to understand the fundamentals of a thermoplastic and a thermoset composite. Now, as I mentioned, the thermoset composite can have rather a continuous sheets, whereas a thermoplastic composite, yes, today we are having with the continuous sheets, but then, as I mentioned, we are also dealing with a direct long fiber injection methodology, like a fixed fiber orientation and, no, and variable fiber orientation and a length distribution, because the injection molding process will pulverize the fibers. So depending on the fiber length distribution and the fiber orientation distribution, the properties of the composite will change locally in a given part. So that's the basic idea behind a thermoplastic composite. So if we are choosing a thermoplastic composite, then we need to do a material selection based on the preceding inputs like performance targets, function, DFMR, cost. And then based on that, we need to generate data for CAE and NVH. Now, the basic CAD has to be taken through a mold flow analysis in case of a thermoplastic composite process that is based on injection molding or variations of injection molding. Now, this mold flow analysis will tell on in a given part how does the fiber orient and what sort of lengths can be expected out of it. Once the fiber orientation is very clear, then we have to actually generate material property data from sheets which are made to simulate that fiber orientation. Now, when we do that, what happens is we get good correlation between the CAE and the actual material data and the performance, final part performance. Then once we get that, then we go for the CAE and NVH verification. And then once we do that, we do the costing. Then once all the cost and the design parameters are taken care of, we say the design is good to go. We give a tool kickoff, and then we get the part, we validate it, and then we go on implementing it. The same thing applies for thermoset composite, but the complexity is not that much as compared to a thermoplastic composite. Thermosets have that advantage of orienting it by varying the layup sequence. So what we call by layup sequence is the way the fibers are stacked one over the above, and then finally we infuse the resin. That's the layup sequence. So when we start, we have that option of choosing the layup sequence, which is a luxury when it comes to thermoplastics, other than the sheet and hard stamping route. So a floor pan can be made out of the thermoset composite by following the thermoset composite methodology, and a front end carrier can be designed and implemented based on a thermoplastic composite design methodology. Moving ahead, what are the key challenges? Yes, the preceding discussion touched upon it. Still, these remain a challenge. The first one is bonding dissimilar materials. Just imagine in a crash, we have 3-4 materials. They have to be together, and separation, delamination, these are not desired. So that still remains a challenge. Of course, people are working on it. Composites repair, yes, that's a new area. We are talking about high-end repair, and we are talking about structural parts. And so we should develop that technology, and it should be matured enough. And then finding local partners, yes, it's difficult because most of these technologies have origins in Europe and the USA, and some are in countries like Japan and Australia. The key point here is how do we bring those technologies from the academic domain to a mass market domain? So yes, that needs a lot of work, but it's a golden age for composites in India, because a lot of raw material suppliers and converters have started digging their heels into it. Now today we have companies that are going to set up carbon fiber manufacturing lines in India. So naturally, we expect this to move in the upcoming years. And then managing the cost, which is a sum total of all the above. That's there because finally, India is a net importer of crude oil. So as the crude price goes up, the polymer prices also goes up, and because of which the cost also goes up. That's the stage today. But then, this is an area that need to be managed, like how we manage other things. So these are some of the challenges that are there with composites. Not to mention that these are the very challenges, especially the cost challenge, that drives natural composite with natural polymers. So that's the whole thing. Now I give it to Dr. Shankar. Thank you.
Thanks, Balaji. Thanks a lot for this very interesting overview of the potential of composite materials and the various innovative applications that they can enable. Thanks a lot. So I'm going to shift gears and talk about a different set of materials that would go into enabling the electric vehicles. So since we are already out of time, I'm going to very quickly go through this. Maybe about 10 minutes is what we will spend on this. And so let me share my screen. So, having heard Dr. Guru talk about the world of automotive materials, the various trends in terms of different new materials coming in, also having heard Mr. Balaji talk about the potential of composite materials and the various innovative applications, let's very quickly talk about the latest in terms of materials that enable the electric vehicles. With this, we would have a fairly good coverage of various materials that are important in the automotive world. So this part of the talk is going to be a little different from the earlier two because those are mostly structural materials. Here we are going to talk about a few functional materials that go into the batteries and the electric motors of the electric vehicles. If you look at the future of mobility, it's going to be a combination of electric, autonomous, and connected vehicle technologies. And if you look at electric vehicles specifically, some of the biggest challenges there are in terms of addressing the anxiety about the range of the electric vehicle, making sure that the battery, the price of the battery comes down, the electric car becomes more affordable. Also providing the charging infrastructure that makes it easy to use the electric car. These are the three big challenges ahead of us in terms of making the transition to electric vehicles. And there are a few technology bottlenecks, and I have listed three here, and two of them are related to materials. And that's a part that we will focus on for today's discussion. One is the materials that go into the battery, the lithium ion battery of the electric car. Here I'm going to talk about two important materials, lithium and cobalt. Then we will talk about the materials that go into the electric motor. These are magnetic materials and these are rare earth materials like neodymium, which goes into the construction of very strong magnets that would enable compact motors for the electric cars. So primarily I will focus the discussion on these two materials, the battery materials and also the magnetic materials for the motors. If you look at the battery material, which is typically a lithium ion battery pack, it's basically about, if you look at a car like the Tesla Model S, that's about 63 kgs of lithium in a typical 70 kilowatt hour Tesla Model S. And in terms of the typical AAA batteries that you're all familiar with, this would be about 7,000 batteries that go together to power an electric car. So what is it that we look for in these batteries are typically the ability to store energy, which we call a specific energy, and the ability to give this energy on demand, which we call a specific power. Then we look at the safety aspects, the performance. We also look at the life of the battery, also the cost. Cost is important because today the cost of the electric vehicle, if you look at, almost half of that comes from the cost of the battery itself. So the battery is what is making it expensive. So we need to look at technologies that can make the battery more affordable. There are various materials that are being looked at in terms of within the lithium ion class of materials itself. There are lithium nickel cobalt aluminum, which is referred to as NCA, lithium nickel manganese cobalt, which is referred to as NMC, lithium manganese spinel LMO, lithium titanate LTO, and lithium iron phosphate LFP. These are some of the popular battery formulations. And each of them have certain properties which are really good and certain properties which could be further improved. So this is a whole gamut of materials that go into the batteries. And if you look at the price of this battery, the price of the battery has steadily fallen down over the years, and almost 87% reduction has happened over the last 10 years, if you look at. And this has been possible through a series of technology innovations that have happened within the lithium ion battery chemistry. And also, it's important for us to know that what we refer to as a learning rate. That is, when we start making more of these batteries, we'll be able to bring down the price of these batteries. For example, every time we double the volume of these batteries, the price would come down by about 18%. So it's also important for us to expand our manufacturing capacity for lithium ion batteries across different parts of the globe. Ideally, if we can reach about $100 per kilowatt hour by 2025, that will be a very, very good position to be in for the mass adoption of electric vehicles. So this has steadily improved, and we are around at 176 as we speak today. And with many more innovations happening in the next 5 years, I'm confident that we should be able to meet this aggressive and ambitious goal of $100 per kilowatt hour. Because many of the technologies that are enabling these storage are exponentially growing technologies, and there has been a very steady improvement in the performance of these battery systems over the years. So these are the materials which get into a wide variety of clean energy and clean mobility applications. And here I have shown a few materials: dysprosium, praseodymium, neodymium. These are all rare earth materials which go into the magnets of the electric motors. Then you see cobalt, manganese, nickel, lithium. These are all the battery materials that go into the construction of the battery itself. So these are some of the important materials, some of which are critical in the sense, in terms of their availability for the next few years. There are going to be concerns around the steady availability of these materials, since it is important for us to know that these materials are important for the scaling up of electric vehicles, and we should be able to mitigate the risks around the availability of these materials. So lithium is one of the ways in which lithium is procured is in terms of it's a salt. So by typically way the salt is made by evaporation, same way the lithium minerals is also acquired. And lithium is mainly limited to three regions in South America: Argentina, Bolivia, and Chile, with relatively smaller amounts in Australia. So that's where, since it is geographically limited in its distribution, there is a lot of concern around the availability of lithium. Of course, if you look at the price, the contribution of each of these materials, you'll see that cobalt contributes to maximum because of its very high price. And cobalt currently comes from only one country, which is Congo. And we need to basically look at how we can mitigate the risk around supply of both lithium and cobalt when we start making more and more electric vehicles. Finally, the motors. We talked about the magnets in these motors. So when we look at different magnetic materials, we find that the rare earth-based materials provide the highest magnetic strength. What this means is, if the strength is high, then we'll be able to make very small, compact motors, which is important for electric vehicles. So we are specifically talking about rare earths like neodymium, praseodymium, and dysprosium. So in the past, these were mined in different parts of the globe, but today the mining of these rare earths is limited to China, and almost all the rare earth materials for all applications come from this part of the globe. So primarily we are looking at two important things: clean energy and clean mobility, for creating a sustainable future. So when we talk about clean energy, we are talking about renewables, solar, PV. And as long as the sun sets in the evening, you definitely need a storage. And that's where the lithium ion batteries come in a very big way for enabling clean energy. And it's the same lithium ion batteries which would be needed for enabling electric cars too. That's how the lithium and cobalt, which enable the battery, becomes very critical for both the clean energy and also the clean mobility industry. If you look at the motor, the rare earths, again, these electric motors are required not only for the electric vehicle industry, but also for the wind turbines also need these magnets for the motors. So again, both clean energy and clean mobility would need these rare earth materials. Then beyond battery and motor, if you look at other applications like the LiDAR for the autonomous and the various sensors and electronics that goes into the connected vehicles, would be looking at semiconductor materials too. So these are the other functional materials over and above the various structural materials and composites that you heard in the first part of the discussion today. So with this, we have covered a fairly good spectrum of materials. We started with a quick introduction to the world of automotive materials by Dr. Guru Rajan. Then we went into a very elaborate discussion on the design and application of composite materials by Mr. Balaji. And finally, we are wrapping up with the materials for electric vehicles, which is primarily lithium and cobalt for the battery and the rare earths for the magnets for the electric motors. So very quick assessment quiz. Mention at least 3 driving forces that are critical for the automotive industry. Mention at least 2 metals and 1 composite technology trends in automotive materials. What are the 2 types of polymer composites that are used in structural parts of an automobile? What is the critical parameter that need to be considered in composite part design? What are the 2 critical elements that constitute the lithium-ion batteries that were discussed today? And finally, what are the rare earth elements that constitute the strong magnets used in electric motors? So these are very easy questions based on what we discussed today. And with this, we would like to wrap it up. So you have my blog and email address for us to reach out. So please send your answers to this quiz to us or to NPTEL. And we'll be able to take all your questions by responding back to you through email. So in the interest of time, we would stop at this stage. And thank you all for being with us today. And I look forward to looking at your questions and responding. All 3 of us would look at the questions and come back to you with our responses. And let me also take this chance to thank Dr. Guru Shankar Rajan and Mr. Balaji for joining me today to give this comprehensive overview to the world of automotive materials. So over to you, Balaji and Dr. Guru, for a quick thanks, and then we'll wrap it up now.
Yeah, thank you. Thanks for this opportunity. It has been a pleasure. And we look forward to the answering the questions. At least I'm passionate about it, so I need to. Yeah.
Thanks. Great.
Thank you, Dr. Shankar. Thank you, NPTEL, for the opportunity to share our knowledge. Hope the engineers, mechanical, electrical, design engineers, when they think about designing a part, they have the material, the performance, the durability, everything into consideration when they select the material. So, thank you.
Absolutely, Dr. Guru. Thanks a lot. Thank you, NPTEL. Thanks. Bye.